the HAL Tejas is a multi-role light fighter under development by India. It is a tailless, compound delta-wing design powered by a single engine. It came from the Light Combat Aircraft Program, which began in the 1980s to replace India's aging MiG-21 fighters. Later, the Lca was officially named Tejas, meaning Radiance by the then Prime Minister Atal Bihari Vajpayee. Tejas has a pure double delta-wing configuration, with no tailplanes or canard, and a single dorsal fin. It integrates technologies such as relaxed static stability, fly-by-wire flight control system, multi-mode radar, integrated digital avionics system, composite material structures, and a flat-rated engine. It is supersonic and highly maneuverable, and is the smallest and lightest in its class of contemporary combat aircraft. The Tejas is the second supersonic fighter developed indigenously by Hindustan Aeronautics Limited after the HAL Marut. The Indian Air Force was reported to have a requirement for 200 single-seat and 22-seat conversion trainers, while the Indian Navy might order up to 40 single-seaters to replace its Sea Harrier FRS-51 and Harrier T-60. The Tejas was cleared in January 2011 for use by Indian Air Force pilots. It received the second of 3 levels of operational clearance on December 20, 2013. Development. Lca Program. In 1969, the Indian government accepted the recommendation by its Aeronautics Committee that Hindustan Aeronautics Limited should design and develop an advanced technology fighter aircraft around a proven engine. Based on a tactical air support aircraft AS markedly similar to that for the Marut, HAL completed design studies in 1975, but the project fell through due to inability to procure the selected proven engine from a foreign manufacturer and the IAF's requirement for an air superiority fighter with secondary air support and interdiction capability remained unfulfilled. In 1983, IAF realized the need of an indigenous combat aircraft for 2 primary purposes. The principal and most obvious goal was the development of a replacement aircraft for India's aging MiG-21 fighters. The MiG-21 has been the mainstay of the Indian Air Force since the 1970s. The Long-Term Re-Equipment Plan 1981 noted that the MiG-21s would be approaching the end of their service lives by the mid-1990s, and that by 1995, the IAF would lack 40% of the aircraft needed to fill its projected force structure requirements. The Lca program's other main objective was to serve as the vehicle for an across-the-board advancement of India's domestic aerospace industry. The value of the Aerospace Self-Reliance Initiative is not simply the production of an aircraft, but also the building of a local industry capable of creating state-of-the-art products with commercial spin-offs for a global market. The Lca program was intended in part to further expand and advance India's indigenous aerospace capabilities. To better accomplish these goals, the government chose to take a different management approach, and in 1984 established the Aeronautical Development Agency to manage the Lca program. Although the Tejas is most often described as a product of Hindustan Aeronautics Limited, responsibility for the development of the Tejas actually belongs to ADA, a national consortium of over 100 defense laboratories, industrial organizations, and academic institutions with HAL being the principal contractor. The Indian government's self-reliance goals for the Lca include indigenous development of the 3 most sophisticated Euro, and hence most challenging Euro systems, the fly-by-wire flight control system, multi-mode pulse Doppler radar, and afterburning turbofan engine. Of the 5 critical technologies the ADA identified at the beginning of the Lca program as needing to be mastered for India to be able to design and build a completely indigenous fighter, 2 have been entirely successful: the development and manufacture of advanced carbon fiber composite structures and skins and a modern glass cockpit. In fact, ADA has had a profitable commercial spin-off in its Atal integrated automated software system for the design and development of 3D laminated composite elements. These successes have gone mostly unnoticed in the shadow of the problems encountered with the other 3 key technology initiatives. Nonetheless, as a result of the accomplishments of India's domestic industries, about 70% of the components in Lca are manufactured in India, and the dependence on imported components used would be progressively reduced in the coming years. HAL serves as the prime contractor and has leading responsibility for Lca design, systems integration, airframe manufacturing, aircraft final assembly, flight testing, and service support. The ADA itself has primary responsibility for the design and development of the Lca's avionics suite and its integration with the flight controls, environmental controls, aircraft utilities systems management, stores management system, etc. Of particular importance are the initiatives to develop an indigenous flight control system, radar, and engine for the Lca. The National Aeronautics Laboratory now called the National Aerospace Laboratory was selected to lead the development of the flight control laws, supported by the Aeronautical Development Establishment. HAL and the Electronics and Radar Development Establishment are jointly developing the Tejas multi-mode radar. The GTRE is responsible for the design and parallel development of the GTX-35 versus K-Very afterburning turbofan engine for the Tejas. The IAF's air staff requirement for the Lca were not finalized until October 1985. This delay rendered moot the original schedule which called for first flight in April 1990 and service entry in 1995. However, it also proved a boon as it gave the ADA time to better marshal national R&D and industrial resources, recruit personnel, create infrastructure, and to gain a clearer perspective of which advanced technologies could be developed indigenously and which would need to be imported. Out of a total of 35 major avionics components and line-replaceable units, only 3 involve foreign systems. These are the multifunction displays by Sextant and Elbit, the helmet-mounted display and sight queuing system by Elbit, and the laser pods applied by Rafael. However, even among these 3, when the Lca reaches the production stage, the MFDs are expected to be supplied by Indian companies. A few other important items of equipment have been imported. As a consequence of the embargo imposed on India after its nuclear weapons tests in May 1998, many items originally planned to be imported were instead developed indigenously. The nuclear test sanctions delayed the development of technologies that were already many years behind schedule. Development history. The Lca design was finalized in 1990 as a small tailless delta-winged machine with relaxed static stability and control configuration to enhance maneuverability performance. A review committee was formed in May 1989 which reported that infrastructure, facilities and technology of India had advanced sufficiently in most areas and that the project could be undertaken. Project definition commenced in October 1987 and was completed in September 1988. Dassault Aviation of France was hired as a consultant to review the PD and provide advice based on its extensive aviation expertise. The phase costed $5.6 billion. It was decided by the government that the full-scale engineering development of the program would proceed in 2 stages. Phase 1 commenced in April 1993, and focused on proof of concept, and comprised the design development and testing of 2 technology demonstrator aircraft which were named as TD-1 and TD-2. This would be followed by the production of 2 prototype vehicles. TD-1 finally flew on January 4, 2001. Fbw Program Phase I was successfully completed in March 2004 and costed $21.88 billion. Phase 2 commenced in November 2001, and consisted of the manufacturing of 3 more prototype vehicles, leading to the development of the final variant that would join the Air Force and the Navy and 8 limited series production aircraft, and establishment of infrastructure for producing 8 aircraft per year. The phase costed $33.0178 billion, and an additional amount of $24.7578 billion was given for induction into Indian Air Force by obtaining IOC and FOC. The total cost for development of Tejas was $79.6556 billion as of August 2013. One of the most ambitious requirements for the Lca was the specification that it would have relaxed static stability. Although Dassault had offered an analog FCS system in 1988, the ADA recognized that digital flight control technology would soon supplant it. RSS technology was introduced in 1974 on the General Dynamics F-16 prototype, which became the first production aircraft to be slightly aerodynamically unstable by design, to improve maneuverability. Most aircraft are designed with positive static stability, which induces aircraft to return to straight and level flight attitude if the pilot releases the controls. This reduces maneuverability as the inherent stability has to be overcome. Aircraft with negative stability are designed to deviate from controlled flight and thus be more maneuverable. Fly-by-wire flight control system has become state-of-the-art technology. Therefore, in 1992 the Lca National Control Law Team was set up by the National Aeronautics Laboratory to develop India's own version for the Tejas. However, Lockheed Martin's involvement was terminated in 1998 as part of an embargo enacted by the US in response to India's second nuclear tests in May of that year. The NAL's CLAW team eventually managed to successfully complete integration of the flight control laws indigenously, with the FCS software performing flawlessly for over 50 hours of pilot testing on TD1, resulting in the aircraft being cleared for flight in early 2001. The automatic flight control system of the Tejas has been highly praised by all of its test pilots, one of whom said that he found it easier to take off with the Lca than in a Mirage 2000. The Lca's maiden flight was made by TD1 from National Flight Test Centre, near Bangalore, on January 4, 2001, and its first successful supersonic flight followed on August 1, 2003. TD2 made its first flight on June 6, 2002. Pilots regarded the Tejas as the IAF's most pilot-friendly fighter. An NFTC test pilot during the IOC ceremony on December 20, 2013 said, "As a multi-role fighter, the Tejas is at least the equal of the IAF's upgraded Mirage 2000. It can more than hold its own in our operational scenario." Another IAF pilot said that the Tejas is better than the MiG-21. Another critical technology area tackled for indigenous development by the ADA team is the multi-mode radar. It was initially planned for the Lca to use the Ericsson Microwave Systems PSO-5 per RIJ band multifunction radar, which was developed by Ericsson, and for anti-defense systems integration for the Saab JAS-39 Gripen. However, after examining other radars in the early 1990s, the Defense Research and Development Organization became confident that indigenous development was possible. HAL's Hyderabad division and the LRDE were selected to jointly lead the MMR program, and the radar development effort began in 1997. The DRDO's Center for Airborne System is responsible for running the test program for the MMR. Between 1996 and 1997, CABS converted the surviving HAL HS-748M airborne surveillance post into a test bed for the avionics and radar of the Lca. By mid-2002, development of the MMR was reported to be experiencing major delays and cost escalations. By early 2005 only the air-to-air look-up and look-down mode euro 2 very basic mode euro were confirmed to have been successfully tested. In May 2006 it was revealed that the performance of several modes being tested still fell short of expectations. As a result, the ADA was reduced to running weaponization tests with a weapon delivery pod, which is not a primary sensor, leaving critical tests on hold. According to test reports, the crux of the problem is a serious compatibility issue between the radar and the Advanced Signal Processor module built by the LRDE. Acquisition of an off-the-shelf foreign radar is an interim option being seriously considered. Engine and propulsion. Initially, it was decided to equip the prototype aircraft with the General Electric F404 GEF2J3 afterburning turbofan engine. Simultaneously, in 1986, a parallel program to develop an indigenous power plant was also launched. In 1998, following India's nuclear tests, US placed sanctions on the sale of General Electric F404 turbofans. It was decided to invest in a domestic jet engine as a replacement of the F404. Cost overruns and delays were encountered while developing the new Kaveri engine. After the lift of sanctions, decision was made to buy additional F404 engines for use on the initial Tejas production aircraft. Led by the gas turbine research establishment, the GTRE GTX-35 Versus, named Kaveri, was expected to replace the F404 on all production aircraft. However, Progress in the Kaveri development program was slowed by technical difficulties. Development snags with the Kaveri resulted in the 2003 decision to procure the uprated F404GE-20 engine for the 8 pre-production LSP aircraft and 2 naval prototypes. General Electric was awarded a $105 million contract in 2004 for development, engineering and production of 17 IN-20 engines, delivery of which began in 2006. The F404GE-20 was trial installed on the Tejas and the engine generated more than 19,000 pounds uninstalled thrust and completed 330 hours of accelerated mission testing, equivalent of 1,000 hours of flight operation. In 2007, an additional 24 F404IN-20 afterburning engines were ordered to power the first operational squadron of Tejas fighters. In mid-2004, the Kaveri failed its high-altitude tests in Russia, ending the last hopes of introducing it with the first production Tejas aircraft. In February 2006, the ADA awarded a contract to the French aircraft engine company Snecma for technical assistance in working out the Kaveri's problems. The Kaveri engine based on Snecma's new core, an uprated derivative of the M88-2 engine that powers the French Rafale fighter, providing 85 kilonewtons of maximum thrust, was being considered a third option by DRDO. This led the IAF to object that since Snecma had already developed the core of the engine, the DRDO will not be participating in any joint development but merely providing Snecma with an indigenous stamp. In 2008, it was announced that the Kaveri would not be ready in time for the Tejas, and that an in-production power plant would have to be selected in the 95 to 100 kilonewton range to allow the aircraft to perform combat maneuvers with optimal weapons load. The contenders were the Eurojet EJ200 and the General Electric F414. IAF sources said that the airframe will have to be redesigned to accommodate the heavier engine, which is to take up to 3-4 years. After evaluation and acceptance of the technical offer provided by both Eurojet and GE Aviation, the commercial quotes were compared in detail and GE Aviation was declared as the lowest bidder. The deal will cover purchase of 99 GE F414 engines. The initial batch will be supplied by GE and the remainder will be manufactured in India under a transfer of technology arrangement. Initial production, further testing. In March 2005, the IAF placed an order for 20 aircraft, with a similar purchase of another 20 aircraft to follow. All 40 were to be equipped with the F404GE-20 engine. In December 2006, a 14-member Lca induction team was formed at Bangalore to prepare the Tejas for service and assist with its induction into service. On April 25, 2007, the first limited series production Tejas accomplished maiden flight, achieving a speed of Mach 1.1. The Tejas completed 1,000 test flights by January 22, 2009 with more than 530 hours of in-flight testing. The Tejas achieved a speed of over 1,350 km per hour during its sea-level flight trials in 2009. These trials were conducted at INS Hansa, Goa. On June 16, 2008, LSP-2 made its first flight. On April 23, 2010, the third production aircraft flew with a hybrid version of the Ultra ELM-2032 multi-mode radar, and by June 2010, the fourth production aircraft took first flight in the configuration it would be delivered to the Indian Air Force in. By June 2010, the Tejas had also completed the second phase of hot weather trials. The objective of the hot weather trials was to prove that the aircraft was in an IOC configuration with the weapon system and sensors integrated. The sea trials of the aircraft are also being carried out. LSP-5 with IOC standard equipment took to skies on November 19, 2010. The trainer variant prototype took to the skies in November 2009. In December 2009, the Indian government sanctioned $80 billion to begin production of the fighter jet for the Indian Air Force and Indian Navy. The Indian Navy has a requirement of 50 Tejas aircraft and the first prototype, NP-1, was rolled out in July 2010. IAF ordered 20 additional Tejas fighters after the Defense Acquisition Council cleared the plan. In November 2010, It was reported that the Tejas Mk1 reportedly fell short of the relaxed air staff requirements stipulated for limited series production aircraft. The areas that did not meet requirements were power-to-weight ratio, sustained turning rate, maximum speeds at low altitudes, AOA range, and weapon delivery profiles. The extent of the deficiencies was classified. Initial operating clearance for the Tejas was awarded on January 10, 2011 by Defense Minister A.K. Antony to Chief of Air Staff Air Chief Marshal P.V. Nick. IOC allows IAF pilots to use the aircraft. The IAF plans to raise the first squadron in Bengaluru to iron out issues with ADA and HAL, and eventually base these fighters at Sula Air Force Station, Coimbatore in the southern state of Tamil Nadu. The weapon tests including bombing begun in September 2011 at Pokhran Range, to be followed by missile firing tests at Goa. Rafael's Derby Fire and Forget missile will serve as the Tejas' initial medium-range air armament. Tejas' final operational clearance was reportedly delayed from December 2012 until mid-2013 or later. The Tejas program has enlisted eːdʒəs to help expand the flight envelope to meet service requirements. On March 9, 2012, LSP-7 took to its maiden flight from HAL Airport. The naval LCA made its first flight, almost 2 years after being rolled out, on April 27, 2012. On June 27, 2012, 3 HAL Tejas aircraft completed precision bombing runs in the desert of Rajasthan, where they deployed a series of weapons, including laser-guided 1000 lb bombs and unguided bombs. The LCA had conducted similar bombing runs in the month of September 2011 at Pokhran. The Tejas had completed 1,941 flights by July 2012. Some defense sources indicate that it will not reach FOC and become fully combat capable until 2015. The Tejas was grounded for over 3 months in the later half of 2012 because new helmets for the pilots extended above the ejection seats. The helmets could have prevented a smooth ejection by hitting the canopy before it was blown off, and represented a serious safety issue, hence flight testing was stopped in August 2012. The ejection systems were modified to rectify this issue, and flight tests resumed in November. LSP-8 had a successful maiden test flight on March 31, 2013, and the program had completed 2,418 test flights by November 27, 2013. On March 31, 2013, LSP-8 took to its maiden flight from HAL Airport. Operational clearance: HAL was instructed by the Indian government to strictly adhere to deadlines to ensure IOC-2 by the end of 2013 and final operational clearance by the end of 2014. On December 20, 2013, the initial operational clearance II of the aircraft was issued, after which it was cleared to be flown by regular pilots of the Indian Air Force and begin induction into squadron service. The first squadron of 18 to 20 fighters will be based at Sula Air Force Station in the state of Tamil Nadu, and it will work to achieve final operational clearance by December 2014. To fulfill the IOC-II standard, the aircraft was certified to carry close to 3 tons of weapons which include laser-guided 500 kg bombs and short-range L-73 missiles, reach top speeds of 1,350 km per hour, withstand turns up to 7 g, reach angle of attack of 24 degrees, and have an operational radius of 400 to 500 km. Cost of a single unit in the IOC-2 configuration is between $1.7 billion and $1.8 billion. To obtain FOC, the fighter will have to be certified for 6 more criteria. Integration of Derby and Python BVR missiles weighing 150 kg, with a range of 70 km, as well as a eːdʒəs Shippenov GSH-23 gun will be undertaken. An air-to-air refueling probe supplied by Cobham will be added. The angle of attack will be increased from 24 to 28 degrees, the braking system will be enhanced, and the existing nose cone radome made of composites will be replaced by a quartz model to increase the current radar range of 45 to 50 km to more than 80 km. These modifications are expected to be completed within 15 months of IOCE. In 2014 the FOC was pushed back as multiple aircraft would need to be tested and the only one produced to date would need further modifications to complete all tests. Design overview. The Tejas is single-engine multi-role fighter which features a tailless, compound delta planform and is designed with relaxed static stability for enhanced maneuverability. Originally intended to serve as an air superiority aircraft with a secondary dumb-bomb ground attack role, the flexibility of this design approach has permitted a variety of guided air-to-surface and anti-shipping weapons to be integrated for more well-rounded multi-role and multi-mission capabilities. The tailless, compound delta planform is designed to be small and lightweight. This platform also minimizes the control surfaces needed, permits carriage of a wider range of external stores, and confers better close combat, high speed, and high alpha performance characteristics than comparable cruciform wing designs. Extensive wind tunnel testing on scale models and complex computational fluid dynamics analyses have optimized the aerodynamic configuration of the Lca, giving it minimum supersonic drag, a low wing loading, and high rates of roll and pitch. Materials used included aluminium lithium, superplastically formed titanium and carbon fiber composite. Tejas employs CFC materials for up to 45% of its airframe, including in the fuselage, wings, elevons, tailfin, rudder, air brakes and landing gear doors. The wing and fin of the compound delta aircraft are of carbon fiber reinforced polymer, and were designed to provide a minimum weight structure and to serve as integral fuel tanks. All weapons are carried on one or more of 7 hardpoints with total capacity of greater than 4,000 kg, 3 stations under each wing and 1 on the under-fuselage center line. An 8th offset station beneath the portside intake trunk can carry a variety of pods like FLIR, IRST, laser rangefinder designator, as can the centerline under-fuselage station and inboard pairs of wing stations. Auxiliary fuel tanks of 800 and 1,200 liters can be carried under the fuselage to extend range. An aerial refueling probe on the starboard side of the forward fuselage can further extend range and endurance. Although 2-seat variants of the Lca are planned, the examples built to date are crewed by a single pilot on a Martin Baker 00 ejection seat. The British Martin Baker ejection seat is planned to be replaced with a locally developed alternative. Tejas requires a very short runway and rockets off the runway and into the air in a mere 500 meters. Airframe. The Lca is constructed of aluminium lithium alloys, carbon fiber composites, and titanium alloy steels. The Tejas employs CFC materials for up to 45% of its airframe by weight, including in the fuselage, wings, elevons, tailfin, rudder, air brakes and landing gear doors. Composites are used to make an aircraft both lighter and stronger at the same time compared to an all-metal design, and the Lca's percentage employment of CFCs is one of the highest among contemporary aircraft of its class. Apart from making the plane much lighter, there are also fewer joints or rivets, which increases the aircraft's reliability and lowers its susceptibility to structural fatigue cracks. The tailfin is a monolithic honeycomb piece, reducing the manufacturing cost by 80% compared to the subtractive, or deductive method, involving the carving out of a block of titanium alloy by a computerized numerically controlled machine. No other manufacturer is known to have made fins out of a single piece. The use of composites in the Lca resulted in a 40% reduction in the total number of parts compared to using a metallic frame. Furthermore, the number of fasteners has been reduced by half in the composite structure from the 10,000 that would have been required in a metallic frame design. The composite design also helped to avoid about 2,000 holes being drilled into the airframe. Overall, the aircraft's weight is lowered by 21%. While each of these factors can reduce production costs, an additional benefit €1 and significant cost savings €1 is realized in the shorter time required to assemble the aircraft in €7 months for the Lca as opposed to 11 months using an all-metal airframe. The airframe of the naval variant of the Tejas will be modified with a nose droop to provide improved view during landing approach, and wing leading edge vortex controllers to increase lift during approach. the levers are control surfaces that extend from the wing root leading edge and thus afford better low-speed handling for the Lca, which would otherwise be slightly hampered due to the increased drag that results from its delta wing design. As an added benefit, the levers will also increase controllability at high angles of attack. The naval Tejas will also have a strengthened spine, a longer and stronger undercarriage, and powered nose-wheel steering for deck maneuverability. The Tejas trainer variant will have aerodynamic commonality with the two-seat naval aircraft design. Flight controls. Since the Tejas is a relaxed static stability design, it is equipped with a quadruplex digital fly-by-wire flight control system to ease pilot handling. The Tejas aerodynamic configuration is based on a pure delta wing layout with shoulder-mounted wings. Its control surfaces are all hydraulically actuated. The wing's outer leading edge incorporates 3-section slats, while the inboard sections have additional slats to generate vortex lift over the inner wing and high-energy airflow along the tailfin to enhance high AOA stability and prevent departure from controlled flight. The wing trailing edge is occupied by 2 segment elevons to provide pitch and roll control. The only empennage-mounted control surfaces are the single-piece rudder and 2 air brakes located in the upper rear part of the fuselage, one each on either side of the fin. The digital Fbw system of the Tejas employs a powerful digital flight control computer made by Aeronautical Development Establishment comprising 4 computing channels, each with its own independent power supply and all housed in a single LRU. The DFCC receives signals from a variety of sensors and pilot control stick inputs, and processes these through the appropriate channels to excite and control the elevons, rudder and leading-edge slat hydraulic actuators. The DFCC channels are built around 32-bit microprocessors and use a subset of the Ada programming language for software implementation. The computer interfaces with pilot display elements like the MFDs through MILS TD1553B multiplex avionics data buses and RS422 serial links. In-flight refueling capability via retractable probes on the aircraft's starboard side, and an onboard oxygen generating system for longer missions. Propulsion. The wing-shielded, side-mounted bifurcated, fixed geometry wide-duct air intakes, can ensure buzz-free air supply into the engine compressor for thrust generation. The original plan was for the Lca prototype aircraft to be equipped with the General Electric F404GE-F2J3 afterburning turbofan engine, while the production aircraft would be fitted with the indigenous GTRE GTX-35 versus K-Very turbofan being developed in a parallel. Continued development snags with the K-Very resulted in a 2003 decision to procure the upgraded GE-F404IN-20 engine for the 8 pre-production LSP aircraft and 2 naval prototypes, and after accelerated trials an order was placed for 24 more IN-20 engines for installation on the first 20 production aircraft. The Tejas Mach II will be equipped with the more powerful GE-F414 engine. Avionics. The Tejas has a night vision goggles-compatible glass cockpit that is dominated by an CSIR-CSIO-developed indigenous head-up display, 3 5-in in multi-function displays, 2 smart standby display units, and a get-you-home panel providing the pilot with essential flight information in case of an emergency. The displays provide information on the key flight systems and controls on a need-to-know basis, along with basic flight and tactical data. The pilot interacts with onboard systems through a multifunctional keyboard and several selection panels. The CSIO-developed HUD, Elbit-furnished helmet-mounted display and sight, and hands-on throttle and stick controls reduce pilot workload and increase situation awareness by allowing the pilot to access navigation and weapon aiming information with minimal need to spend time head-down in the cockpit. The Tejas is equipped with both GPS and a ring laser gyro-based inertial navigation system. For flying in poor conditions, an instrument landing system and a ground proximity warning system based on the terrain-referenced navigation system is also employed. The Lca also has secure and jam-resistant communication systems such as the IFF transponder interrogator, VHF-UHF radios, and air-to-air air-to-ground data links. The ADA Systems Directorate's Integrated Digital Avionics Suite integrates the flight controls, environmental controls, aircraft utilities systems management, stores management system, etc. on three 1553B buses by a centralized 32-bit, high-throughput mission computer. Radar and sensors. The Pulse Doppler multi-mode radar is designed to keep track of a maximum of 10 targets and allows simultaneous multiple target engagement. Jointly developed by the LRDE and HAL Hyderabad, the MMR is to perform multi-target search, track while scan, TWS, and ground mapping functions. It features look-up-look-down modes, low-higher pulse repetition frequencies, platform motion compensation, Doppler beam sharpening, moving target indication, MTI, Doppler filtering, constant false alarm rate detection, range Doppler ambiguity resolution, scan conversion, and online diagnostics to identify faulty processor modules. While originally planned to be fitted on the initial production aircraft, delays in the MMR's development prompted the DRDO to cooperate with Israel Aerospace Industries to integrate a hybrid version of the ELM 2032 radar on the Tejas. The ELM 2032 radar used in LSP-3 has a detection and tracking range of up to 150 km in air-to-air mode. The air-to-ground mode generates high-resolution radar imagery of locations at up to 150 km, and air-to-sea mode can detect and classify naval targets at ranges of up to 300 km. The development of an active electronically scan array radar is expected to begin pending the selection of a developmental partners between DRDO foreign partners. Prospective partners include Europe's Airbus Group and Israel's Alta. The initial contract is to involve the co-development of 10 prototypes. Tejas is also to be equipable with an infrared search and track sensor, which can detect and track thermal energy emissions. This system shall be pod-based. Additional sensor pods are to include a drop tanks for ferry flight extended range loitering time, FLIR targeting pod, ECM pods, flares infrared decoys dispenser pod and chaff pod, EOIR sensor pod, lightning targeting pods forward-looking infrared sensor, and a laser rangefinder designator, which can be used in various capacities, including reconnaissance, training, or attack. Self-protection. The electronic warfare suite is designed to enhance the survivability during deep penetration and combat. The Lca Zw Suite is developed by the Defense Avionics Research Establishment with support from the Defense Electronics Research Laboratory. This EW Suite, known as Manoeuvrable, includes a radar warning receiver, missile approach warning and a laser warning receiver system, infrared and ultraviolet missile warning sensors, self-protection jammer, chaff, and flares dispenser. An electronic countermeasures suite and a towed radar decoy. In the interim, the Indian Ministry of Defence has revealed that an unspecified number of EW suites had been purchased from Israel's Lca for the Lca prototypes. Stealth features have been designed into Tejas. Being very small, there is an inherent degree of visual stealth, but the airframe use of a high degree of composites, a wide duct inlet which shields the engine compressor face from probing radar waves, and the application of radar-absorbent material coatings are intended to minimize its susceptibility to detection and tracking by the radars of enemy fighters. Operational history. The work to raise the first squadron started in July 2011. The Tejas will be inducted into the 45th Squadron, the Flying Daggers, and will be based in Bangalore before being moved to Sula. The squadron will initially consist of 4 aircraft SP-3 to SP-6. The IAF's Aircraft and Systems Testing Establishment will receive 4 aircraft already built, the SP-1 and 2 and LSP-7 and 8. The final operational clearance campaign began in December 2013, with 3 aircraft from Tejas flight line successfully completing advanced weapon trials. The campaign was held in Jamnagar. New weapons were integrated on the aircraft. As part of the FOC, aircraft is being readied for all-weather trials in Bangalore. 1 aircraft is also being readied for night flying with upgraded systems and software. Plans are afoot to take Tejas for hot weather trials in Gwalior next month, the trials official added. Tejas had taken its maiden flight on January 4, 2001, and as of December 2013, It had completed 2,587 sorties covering over 1,750 hours. Variants. Prototypes, aircraft already built and projected models to be built. Model designations, tail numbers and dates of first flight are shown. Technology demonstrators, TD1 Euro January 4, 2001, TD2 Euro June 6, 2002, prototype vehicles, PV1 Euro November 25, 2003, PV2 Euro December 1, 2005, PV3 Euro December 1, 2006. This is the production variant. PV4, PV5 Euro November 26, 2009 Eurofighter trainer variant, naval prototypes, NP1 Euro 2-seat naval variant for carrier operations. Rolled out in July 2010. NP1 made its first flight on April 27, 2012. NP2 a Euro single-seat Lca Mk1 naval variant for carrier operations. Both NP1 and NP2 are powered by GE404 engine. NP3 and NP4 a Euro single-seat Lca Mk2 naval variant for carrier operations to be powered by the GE414 engines. The design work on the two aircraft is nearly complete. NP5 a Euro another single-seat Lca Mk1 naval variant is planned so as to enhance the pace of certification process for naval Lca. Limited series production aircraft, currently, 8 LSP series aircraft plus 40 aircraft are on order. LSP-1 a Euro April 25, 2007. This Lca is powered by F404 F2J3 engine. LSP-2 a Euro June 16, 2008. This is the first Lca fitted with F404 IN-20 engine. LSP-3 April 23, 2010. The first aircraft to have the hybrid MMR radar and will be close to the IOC standard. LSP-4 a Euro June 2, 2010. The first aircraft that was flown in the configuration that will be delivered to the Indian Air Force. In addition to the hybrid MMR, the aircraft flew with a countermeasure dispensing system and an identify friend or foe electronics system. LSP-5 a Euro November 19, 2010. IOC standard, with all sensors including night lighting in the cockpit, and an autopilot. LSP-6 a Euro will be used to increase the angle of attack, as well as develop better RAM coating to further reduce its radar signature. LSP-7 a Euro March 9, 2012. APU intake has been aerodynamically reshaped. LSP-8 a Euro first flight trial completed in March 2013. LSP-8 is the version that will go for production. SP-1 to SP-40 a Euro planned to fly by late 2013. The SP-1 and SP-2 will be part of No. 45 Squadron that will be based initially in Bangalore, Karnataka. A Euro OE the first SP-1 is in advanced stages of equipping and we will have the ground run by end of June. The SP-1 should start flying by August. The second, third and fourth production aircraft are in various stages of structural build and we hope to deliver 4 aircraft in the current year to the Indian Air Force, a Euro HAL chairman Chiaji said on May 29, 2014. Planned production variants, Tejas trainer a Euro 2-seat operational conversion trainer for the Indian Air Force. Tejas Navy a Euro twin and single-seat carrier-capable variants for the Indian Navy. The Lca's naval variant is to be ready for carrier trials by 2013 and is slated for deployment on the INS Vikramaditya as well as the Vikant-class aircraft carrier. It will be equipped for carrier operation with ski-jump takeoff and arrested landing. It will include strengthened airframe and landing gear and the nose is drooped for better cockpit vision. Tejas Mark II, featuring the more powerful General Electric F414 GEINS-6 engine with 98 kN of thrust and refined aerodynamics, the Mark II is being developed to meet the Indian Air Force requirements and will incorporate fifth-generation fighter elements which are intended to make way into the FGFA and AMCA. The Tejas Mk2 will now have a length of 14.2 meters, height of 4.6 meters and a wingspan of 8.2 meters, same as that of the Tejas Mk1, that, however with an increased wing area. external stores capacity will be boosted to 5,000 kg, while the twin internal air intake ducts will be minimally enlarged to cater to the increased airflow requirements of the 98 kN thrust F414 GEINS-6 turbofan built by GE Aero Engines. The Ministry of Defense had, last January, sanctioned $542.44 million for ADA to develop the IAF's Tejas Mk2 variant and the Indian Navy's Lca Mk2 variant. The IAF is committed to procuring an initial 83 Tejas Mk2s and the Indian Navy has expressed its firm requirement for 46 Lca Mk2. Tejas Mark III Tejas Mark III is a planned version. It is to be stealthier than Mark II and have composite usage up to 70% of the aircraft. The aircraft is to be powered by Kaveri engine once the development of the engine is completed. It is to also feature reduced heat signature. Operators, Air India, Indian Air Force, a Euro 40 Lca Mk1 aircraft plus 8 limited series production aircraft on order. Plans to order 6 squadrons of Lca Mk1 and 4 squadrons of Lca Mk2 aircraft after completing production of Lca Mk1. The IAF was considering at least 14 Tejas squadrons with 294 aircraft as of February 2014, with each squadron to have 21 aircraft. Indian Navy Euro signed an order for 6 naval LCAs at an approximate cost of $31.09 a million per aircraft. The Indian Navy has a requirement for 40 Tejas aircraft. Specifications. Data from tejas.gov.in. RDO Tech Focus, Aero India 2011, General Characteristics, Crew, 1, Length, 13.20 am, Wingspan, 8.20 am, Height, 4.40 am, Wing Area, 38.4 m², Empty Weight, 6,500 kg, Loaded Weight, 9,500 kg, Max Takeoff Weight, 13,200 kg, Power Plant, 1 F404GE in 20 turbofan, Dry Thrust, 53.9 kN, Thrust with Afterburner, 89.8 kN. Internal fuel capacity, 2,458 kg, External fuel capacity, 2x 1,200-litre drop tank at inboard, 1x 725-litre drop tank under fuselage. Performance, maximum speed, Mach 1.6 calibrated airspeed at high altitude, reached in testing of IOCI, theoretically capable of Mach 1.8, range, 850 km, combat radius, 1,300 km, ferry range, 3,000 km, theoretically capable of 3,500 km, service ceiling, 15,000 am, wing loading, 247 kg mass squared, thrust weight, 1.07 grams limits, plus 8/A 3.5 g, armament, guns, 1 mounted 23 twin-barrel GSH-23 cannon with 220 rounds of ammunition. Hardpoints, 8 total, 1 beneath the portside intake trunk for targeting pods, 6 under wing, and 1 under fuselage with a capacity of 4,200 kg. External fuel and ordnance, missiles, air-to-air missiles, Python 5, Derby, Astra, Vimpula 77, Vimpula 73. Air-to-surface missiles, KH-59ME, KH-59MK. Anti-ship missiles, KH-35, KH-31. Bombs, Source KAB-1500L laser-guided bombs, GBU-16 Paveway 2, FAB-250, ODAB-500 fuel-air explosives, ZAB-250-350ths incendiary bombs, BETAB-500 SHP-powered concrete piercing bombs, FAB-500T dumb bombs, OFAB-250-270 dumb bombs, OFAB-100-120 dumb bombs, RBK-500 cluster bomb stake. Others, S-8 rocket pods, Bofors 135 on rocket, drop tanks for ferry flight, extended range loitering time. Lightning targeting pod. See also, HAL Tejas timeline, related lists, list of fighter aircraft, references, notes. Citations Bibliography. External links, Official Tejas site, Features and Analysis, Flying into the Unknown A feature by the Hindu on the Tejas test pilots. Lca and Economics by Sunil Sainis and George Joseph, The Light Combat Aircraft Story, by Air Marshal M.S.D. Woolen. The Case to Support the Indigenous Lca Program, by Ashok Parthasarathi and Raman Pai. Technical, An Approach to High AOA Testing of the Lca, Development Flight Testing of the Tejas Light Combat Aircraft, Lca Avionics and Weapon System Mission Computer Software Development, A Case Study, General, Tejas/Light Combat Aircraft, Fighter-Planes.com, Dawn of Tejas Aero India Special Report from FlightGlobal.com.